lecture for CSC 103, How Computers Work. And in this lecture, I'm going to concentrate on two important concepts in computers, computer science, the von Neumann bottleneck and Moore's law. And both of them have now become familiar enough to the general public that you will see it often listed in newspapers or mentioned on TV in the news whenever there's a technological achievement, a technological achievement. So I thought it'd be nice to cover these two. So von Neumann bottleneck first, and Moore's law, and in particular something that we see fairly often, which is whether Moore's law is dead or not. And we'll see that we've been following Moore's law with computers for a long time, and many people have mentioned that we were not anymore, while other scientists think that it's still going on. So we'll look at that. So here's an example of an article in the New York Times, where we see the sentence highlighted in yellow here that says that the von Neumann bottleneck describes the slowdown in performance that comes from, etc. And you see this appearing in the New York Times, appeared in 2011 in October, so fairly recent. And so it's mentioned there, and it's directly connected to what we have seen in this course. So we're going to take a look at that. So here is von Neumann, and he's responsible for actually many achievements, mostly in mathematics, but also in computer science. He was born in 1903, died in 1957. He's Hungarian-American, and his contributions have been really, really amazing. He worked on the Manhattan Project during World War II, so really was in touch with the best scientists of the time, and allowed him to work with teams of people who were designing new computers. And in 1945, he wrote a very important paper, which was never published, called the first draft of a report on the Edvac, which was a computer being built. And that paper got major distribution without ever being publishing. People passed it around, and it has influenced the way computers are designed today. So here is what that report actually contains. By the way, it's available. You can, if you search for it, you're going to find it on the web. People have retyped it nicely, and you can look at it. What is important to look at, I think, is the table of contents. But what it contains is a very, very detailed description of what he mentioned to be a very high-speed automatic digital computing system. And the architecture that he proposes is interesting. So it's shown here. So in this paper, he proposes that there should be two particular units. And unit in this case means electronics, so boards that carry a particular carry out a particular function. So there should be an arithmetic unit, so a unit that will work on numbers and do arithmetic, addition, subtractions, and operations such as these. A control unit, and a control unit, we have seen what a control instruction is. It's an instruction that allows the computing system to somehow divert from the sequential access to memory. So by default, a processor will be very good at going through memory one cell at a time, one after the other, sequentially, and read all the information that is there. But every so often we may want it to go back to a particular location. So we'll refer to that as control, where we change somehow the sequential nature of a program. So two units, arithmetic unit, control unit, an input unit, an output unit, and that's for providing information to the computer or for getting some of the results. And at that time, there were different ways of doing that, mostly switches and printers, and a memory unit that would contain the information that the computer would work on. And also, he added to this design the fact that that particular organization should have a slow memory unit, slower than the memory unit, and maybe not necessarily electronic, where information could be stored for a long time. So long-term storage for this system. Well, it is interesting that in here it suggests that the information should be stored in binaries. It's really a departure from all the efforts that have been done up to then, recognizing that because of Shannon, operations with Boolean logic can be used for carrying out arithmetic operations, binary addition, for example. So that's a very important detail. And the other one that has stuck until now is that he suggests that the information that is stored in memory, the programs that this particular system is going to work on, will contain both the instructions and the data. It's one of the first times where he sees value in grouping together these two different things and put them together and organize the control unit in such a way. So for the first time here, he suggests that the memory unit should contain both the code and the data. And until then, it had been stored in very different areas where you would have all the control instructions in one place and then the data stored separately. And he suggests that they should be stored together. So if you look at today's computer, so that's a very simplified representation of a motherboard that you're going to find in a regular desktop computer. You will find the motherboard. There will be some tiny little boards stuck in there which represent the random access memory. There will be a central processing unit. The CPU contains what von Neumann referred to as the arithmetic unit and the control unit. So now we have it in one chip. And you have the input-output devices. So you have the CPU, you have the memory, you have the input-output devices. We call them today I/O devices, I for input, O for output. So typically these are the places where you're going to connect cables in. And then, interestingly, the slow memory, we do have it as well. That's the disk. So the disk is the slow memory that stores information that normally goes in RAM, but when you turn off the power of your computer, everything that is in RAM disappears, so you have to store it in a slow external memory. So it's external to this system. Usually it is inside the same device, the same box, but it is there. So it's remarkable that somebody in 1945 proposes a design that we have followed until today. So really, today our computers are designed the exact same way. And if you're not sure of that, or if you don't think that affects you, well, your laptop, your tablet contain computers that have a processor and memory and I/O devices, and even a phone. So this is a picture showing a regular data phone and the motherboard inside. So the motherboard is maybe shaped slightly different from what you would expect, but if you were to look carefully at the different parts, we would recognize the processor, we would recognize memory. And there's slow memory. The SIM card is actually a slow memory that stores some information that would be volatile. So even something like this is a computer that follows the von Neumann architecture. It's quite remarkable. So if you look at today's processors, so remember what we're after. We want to understand what people have referred to as the von Neumann bottleneck. So today's computer, we have a processor, so the typically what we're going to find inside, I'm simplifying here a great deal, but we have registers shown here as AC and PC. And a little plus here is to indicate that there's a part of the processor that is in charge of doing arithmetic. So control unit and arithmetic unit are in there. And whenever the processor accesses memory, it has to provide an address that is fed on this arrow here, which is basically a collection of wires. So the processor will have to send in a number, which is the address of a particular location that it wants to absorb. So binary information is going to go on wires to the RAM, and the binary information that is found there will go on separate wires back to the processor. So these arrows here, this collection of wires, we call them buses. And whenever you look at the motherboard of the computer, you're going to see actually that you have wires connecting the different elements. So here, this is a very simple way of representing such information. So the first bottleneck that exists, if you think about it, the first, so for finding Neumann bottleneck actually corresponds to several different problem areas. So a bottleneck is really something that is going to slow down the flow of, typically in a bottle, the flow of liquid. If there were no bottleneck in a bottle, the liquid would flow much faster, would flow directly out. And the end of the bottle really limits the flow of the water out, or the liquid. And it's the same thing with computers. A bottleneck is something, a design flaw, if you will, that somehow prevents the system from going at the maximum speed. And usually when you have a bottleneck somewhere in a system, the whole system is going to be limited by that bottleneck. Even though a lot of parts may work very, very fast, if there's one of them that is fairly slow, then that's the one that is going to dictate the performance of the whole thing. So the first bottleneck, the first limitation imposed by this architecture is that both code and data are in the memory. And the processor cannot do anything without getting an instruction, which usually will instruct that processor to work on some data. So it has to go and fetch both of these, one after the other, in order to perform some operation. And so that's the first problem, if you will, is that it would be probably much faster if the code and the data were in separate areas of memory, or in separate memories, so that there could be separate sets of buses, one for the code memory and one for the data memory, and code and data could be fetched at the same time. So that's the first source of slowdown, if you want. We're not going as fast as we can because of this. So even though it is a great design, and if you think about it, the fact that code and data live together in memory means that a file, a program, can be given as one unit. You get a CD-ROM or a USB drive, and the file there could be a program that you can run. It will contain both the code and the data. So it's a very easy way to package information and to transport it, or to send it over a network, for example. You can send both the code and the data. So it has a lot of advantages, but what we're describing here is a limitation that is generated by that. So that's the problem, is that if you have instructions and you want several data, pieces of data that you want the processor to work on, do some operation, then you have to fetch the instruction and the data separately, one after the other. So you have a slowdown due to that. So actually here, the second bottleneck is due to the fact that the data that the processor needs to work on, so the data could be, for example, a document that you have typed, Microsoft Word. So the code could be instructions in the Microsoft Word, actually, the program, and the data could be text that you have typed, and you may want to spell check it. That means that somehow the code there, the program, the spell checker will have to have the processor look at every character in the text and somehow look at each one and decide whether, and compare that to a dictionary that will have somewhere else in memory, and will decide whether the words are correctly spelled or not. So if you think about it, everything that is there, that data, the processor, if it's there, it means that the processor will need to access it at some point or the other. There's no other entity in the computer that will be running the spell checker. Spell checker will have to be run on the processor. It's the same thing for other programs that you may use. You may use a spreadsheet, for example, and in your spreadsheet you have some numbers that will be crunched together and some arithmetic done on them. That means that all of these numbers somehow at some point or other have to be sent to the processor where some operation has to be performed, and then they have to be sent back to memory. So the processor by itself becomes the bottleneck. And the analogy that we can make that is quite remarkable is that imagine that every memory cell in memory is the size of a penny. So here I'm going to go back here. So, imagine that this is the size of a penny. And so in general, the data, the blocks in memory have the same size as the registers in a processor. And there's one register, the accumulator, that will be in charge of receiving the data and working on them. So imagine that this is the size of a penny. This is the size of a penny. This is the size of a penny. If you look at the size of today's memory, like in your notebook, in laptop, if you may have 4 gigabytes of memory or 8 gigabytes of memory, which translates in 4 billion words of storage, or 8 billion words of storage. If you have 8 billion pennies and you put them side by side on a surface, you will get roughly the size of a football field. So here you see a football field. So if you were to represent the amount of storage by using pennies, you would get a huge amount of memory. However, the size of your processor would just be a few pennies. So this is the other source of bottleneck, is that you have a huge amount of data, important data in your memory, and because it's there, it will have to be processed in some ways by the processor. There's no other device in the computer that is in charge of looking at modifying the data and storing it back. So imagine a hand holding a few pennies somewhere, somebody holding a few pennies right here. That's the size of the amount of storage in a processor, and all these pennies that are here somehow have to be fetched by the processor, operated on, and stored back. So that it's a huge, if you think about it, it's an incredible small device and a huge amount of storage area that is required. And we've been very, very greedy with memory and computers, and we always want more memory. We always want our new computers. If we buy a new computer, we're going to get more, probably twice as much as what we had before, maybe 4 times as much memory. So this storage is getting bigger, and as it's getting bigger, it's also getting slower. So we have this strange situation where the technology is evolving, and it's easier to make bigger memory and to sell them cheaply, so therefore we can find them in laptops. We can also make processors faster, but the processors are getting faster, better than memory. So the memory is getting slower, even though it's getting faster. In retrospect, or compared to a processor, it's not improving as much. So when the speed of a processor could, for example, double, and the processor can process twice as much data in a particular amount of time, then the memory will improve in access and storage, but not as much as twice. So we have this distance separating processor from memory, and that's the third bottleneck. So people have looked at different solutions for addressing the bottleneck, and one that they found is they've put, so engineers and Intel in particular, they have put cache memory, which is a small memory, inside the processor. And this one is extremely fast, but also very small. It cannot store the same amount of data in very fast memory. So this one is quite slow compared to this. And by doing that, then we allow the processor, this electronics here that is pretty fast, to work with similar electronics that is built on the same piece of silicon. So the technology used for designing this memory is the same technology used for designing the electronics for the registers and the arithmetic unit that is here. So therefore the transistors used everywhere here have the same speed, and we can have a very, very fast system. However, information in this cache has to come from this memory that is very slow compared to the cache, maybe 100 times slower. And so there needs to be some kind of clever system for organizing the data And what has been done is to organize this memory very similarly to what you would do if you were to keep a collection of books in your office or in your dorm, in your room. Assume that you start the semester and you have a shelf where you're going to put books and it's completely empty. And as soon as you have a particular homework assignment that requires you to use a book, then you go to the library. So the RAM in this case would be the library. You're going to go and get some data, some book. And so it takes a long time to do that, and the processor will have to wait. And then when the data arrives, the processor can use it, but a copy of it is going to be kept right here. So that the next time, the next week, when you want to use that same book, well, you don't have to go to the library and spend 45 minutes to an hour going there and looking for the book and getting it. Then it will be right there on your shelf, in your office or in your dorm. So you have a much faster access. And at some point, as the semester is progressing, you're going to find that all the books that you're needing, you will have fetched from the library, brought on and put on your shelf, and everything that you need will be stored right there. So this is kind of a clever system to organize, and engineers have been very, very good at organizing cache memories. So that has been one answer to try to respond to this bottleneck. And another solution for the von Neumann bottleneck is that at some point engineers have discovered that they could shrink the electronics so much that they could put two processors on the same chip. And they decided to do that. So now, instead of having only one processor that has to process all the data in RAM, you have two of them running separately, and they can execute different programs, or the same program and work on different data. So by having two processors, and in this case they're called core, so that's where the term dual core or dual core processor comes from. So now you can have separate cores inside the processor that will run different programs and work on different data. And each one will have its cache. So that means that most of the time the cores will be working with information that they have in their little cache memory. And every so often one of them will need something that it doesn't have. So it will have to go to main memory, fetch the data that it needs, bring it back into the cache. So there won't be too much conflict on these as long as these cores have been have initialized nicely their little cache memory. So nowadays you have processors with 2 cores, 4 cores, 8 cores. Well, when we talk about the Moore's law, we'll also talk about the fact that one reason that is we're not going to get more than 8 to 12 cores in processors, even though we might be able to put more. So the number typically is going to stay around 4 or 8 in modern computers for a while anyway. So that's the reason here in these two graphs. What I'm showing is experiments that researchers have conducted, and they've looked at the performance of systems, the amount of information processed with 1 core, 2 cores, 3 cores, 4 cores, 5 cores. So of course there's no hardware that contains that many cores, but you can simulate it. So people have written computer programs that simulate other computers and with different features, for example different cores. And they looked at how efficient these different computers are. So let's take a look at this. So the x-axis here lists the performance that would be associated with, say, Ed core here. And right here on the y-axis, we see the amount of information that is being processed. So if you have 1 core, you have 1 unit of information that can be processed. If you have a processor with 2 cores, you see that you can get about twice as much information processed in the same amount of time. So having 2 cores is a great benefit. So that means that programs will take typically half the time because you'll have 2 cores. So That's great. If you have 3 cores, however, you see that you don't get to 3, you get to 2.5. And that curve here, instead of continuing like this, it really starts to plateau. And you see here, for example, if you have 8 cores, then the amount of information that you can process is about 4.5 times what you can do with 1 core. So you see that if you have 8 cores, you can really at best do 4 times better in terms of speed of execution. And what this curve shows is that after 8, it really doesn't matter if you have 10, 12, 16, or 20 cores, the amount of information that you're going to be operating on, that you'll be able to process, will be roughly 5 times what you would do with 1 core. So there's a plateauing. So that's something that is due to the fact that when you have so many cores, they're going to collide when they try to go to memory. They will all want at some point to go to memory, and they're going to have to be slowed down because there's only one set, let's go back, there's only one set of buses connecting the processor to memory, and if you have 8 units in here that are trying to access data at the same time, they all have to use the same wires, and that's going to create a bottleneck here to have more. So even though this is a nice solution for the von Neumann bottleneck, it works only to a point. It works only for like 2, 4, and 8 cores, but after that it doesn't pay to put more cores. That's really one reason that nowadays when you buy the top-of-the-line laptop or the top-of-the-line desktop, you're going to have 4 to 8 cores in your processor, but not more, because it doesn't pay to have more. You're not going to get more performance. And this curve is actually even worse. It was another experiment that was done, and here it's the same kind of information, same kind of experiment as this. And what is interesting is this red line, and it shows the amount of information processed when you go from 2 cores to 4 cores, and you see that there's a nice improvement. So going up is good, you process more information. When it stays flat means that you process the same amount of information, whether you have 4 or 8. And here in that particular experiment that they conducted, you see that the performance goes down, and as you're adding more processor cores, then that computer is processing less and less data. So it's really, when these graphs started appearing 10 or so years ago, people were really panicking, because it meant that putting more cores into a processor, which we knew the technology was going to allow us to do, thinking that 32 was going to be possible in a few years, because that's the way electronic technology goes with processors and memory devices. And these experiments show that, well, it's not something that should be done, because the performance is not going to be achievable. You're not going to be going 32 times faster if you have 32 cores. You may go 4 times faster. So it definitely, and actually here, we see that at 64, your performance is much less than when you had 2 cores. So it shows that around this point, around 16, you're doing as well, you're processing as much information as when you have 2 cores. But when you have 32 cores, you're processing actually much less. So not a good way to spend money in a computer. All right. A third bottleneck that is linked to this is that this processor, when it works at a particular speed, and that's what you notice when you buy a computer, or when you look at the specifications of a computer, you will see that it will say something like 2 gigahertz processor or 4 gigahertz processor. So 2 or 4 is typically the maximum clock speed that we have these days, and that indicates how fast the processor can actually work on one number. So if you want to do an addition, you want to add 2 numbers together, how fast will that be? How fast will this operation be? Well, it's given by a little device in a computer that generates a very high frequency signal, tick, 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 very fast to the processor. Similarly to a conductor directing an orchestra, that little clock device sends a signal everywhere inside the computer to give them a rhythm, to say, okay, on the next tick, you're going to all be doing something. And so processors follow this little device. And right now, the speed of this clock is getting towards the end. We really having a hard time making this little device faster. So for a long time, engineers have been able to generate new processors that have a faster clock speed, so they can run faster. And now we're reaching the end. So this particular design, where you have one processor that is kind of like the one organizing how information is being processed, and is driven by this clock signal, we're getting toward the end of it being able to go faster. So we're kind of reaching the end. So the limits typically are about 2 gigahertz. So a hertz, 1 hertz, the definition of a hertz is it has to do with frequencies. 1 hertz corresponds to 1 tick per second. 1000 hertz, we call that 1 kilohertz, is 1000 ticks per second. 1 megahertz is 1 million ticks per second. And 1 gigahertz is 1 billion ticks per second. So typically these days, your laptop, if you have a fairly recent laptop, you will see that the processor inside may work at a frequency of 2 billion ticks per second. So typically it will execute 2 billion instructions in 1 second. And servers, which are bigger machines, and they usually don't have a keyboard, they don't have displays. Typically they will work a little faster, around 4 gigahertz, but that's the limit of today's, and we don't see it getting any better. So we cannot foresee right now having laptops that work at 4 gigahertz or 8 gigahertz in the next 5 years. So that's one of the limits that we have today. So what are the implications of all this? So what it means is that we've had a design that has evolved since 1945, or another way of saying, we have had guidelines for designing computers that people and engineers have followed since 1945 when they were designing new computers. And manufacturers like Intel have followed that up, and they've been very aware of the von Neumann bottleneck. They've been very aware that there were limitations, and they've tried to address them. They've put different cache memories, and sometimes in some of the processors you will find several layers of cache memories inside the core, outside the core. But I mean, inside the core, yeah, outside the core, but inside the processor. Many different ways to try to make the information as readily available to the processor as possible. Try to prevent the processor from having to go to main memory. That means that constantly now researchers are investigating new designs to get out of that von Neumann mold. Von Neumann has been great and has allowed us to really create beautiful machines that do incredible things. If you think of what you can do with a computer or with a phone, data phone, it's quite remarkable. And by the way, we also have computers in other places like cars. A modern car now has tens of computers inside associated with the brakes. They will monitor the amount of gas going into the engine. They will make sure the engine works at its peak performance. All this is done with computers. So we've really done very well with this, but it has limits. So constantly designers, engineers, researchers at universities and in companies are looking at ways to design computers differently that would offer faster performance, a way to write programs and execute programs that would be much more efficient. So the key here that you're going to see in all these new design often is parallelism. So try to do many things at the same time, many processors, many memory banks, But people are also looking at different technologies, not using silicon, using, so you may have heard of quantum computing, so using really different ways. And IBM has been actually now, if you want to do some, if you want to program operation on a quantum computer, IBM has a website where you can go and type in your program and run it, and it will be run on an architecture that is not a von Neumann. It's not using silicon devices, but using quantum mechanics for the info operations. So the main challenges is that we know that the hardware has to change. However, we have a huge amount of software that has been created for computers, and we have a very well specified interface that we like for dealing with computers. We want to be able to have a keyboard or a mouse or some kind of device, a pen that we can use, a screen that can be tactile or not. So and we also have we have a whole generation of programmers, people who know how to write program in a very logical way, in a particular way, using particular languages. So if there's ever a new architecture available, then somehow we don't want to throw away all the software that we'll have written. And we also want people who can directly and very quickly adapt to the new hardware. So that's going to be an enormous challenge, to create a new architecture, discover a new architecture, but somehow make it still compatible with the current ways of programming that we have and the current ways of interfacing with computers that we have. So, and it might be very likely that we'll have a hybrid kind of system at some point, where part of the computer will be the computer that we know with a keyboard, a screen, some electronics in there, and maybe some totally different technology that will interface to that shell and allow us to be able to process information much faster. All right, so that's a quick introduction to the von Neumann bottleneck. So I'm going to move now to Moore's law. So we're going to talk about another important concept in computer science that we will see probably referenced more often than von Neumann bottleneck in trade journals and also in public newspapers like New York Times or others. So I'm going to take a look at Moore's law. And that name comes from Gordon Moore, who is still alive, was born in 1929, studied at Caltech, and very early on started the company named Fairchild, and left Fairchild with 6 others, or in a group of 6, and founded Intel, the company Intel that has been really instrumental in the development of personal computers. So the first IBM PC, for example, used an Intel processor, and so now most computers these days have Intel processors. Phones don't, but a lot of the personal computing devices are based on Intel processors. So anyway, so he's retired. So he's chairman emeritus of Intel and lives in California. And Moore's law comes from a request that he received in 1965 to try to predict the future of personal computers and electronics and a number of transistors in processors. So his job was to look at what had happened in the field and how transistors had been mastered, if you want. The technology of building transistors had allowed engineers to shrink them and make them work faster while limiting the amount of heat that they generate. So he was asked to predict the growth for the next 10 years, and he did. And he found this really remarkable property, and we're going to look at that. And unbelievably, this growth, this particular pattern that he observed, just in a few years of Intel's growth, has continued until now. So And actually other people like Ray Kurzweil, who used to work at MIT and now is at Google, has used this law and showed that actually it covers a lot of the evolution of technology. So we're going to take a look at that. That's Moore's law. So in order to better understand what this is, we can start with a nice story. And the story is that of a sultan who once decided to be very generous with, I guess, a prisoner. And told the prisoner that whatever his wish was, the sultan was going to be good and make it true. And the prisoner apparently was a mathematician, and he said, "Oh, it's very simple." He saw that the sultan had a chessboard in front of him. Said you can put 1 grain of rice on one of the cells, and then 2 grains of rice on the next one, 4 grains of rice, 8, 16, 32, 64, and then keep on doubling the number of grains, and whatever amount you get, then that will be his gift. And Sultan said, "Sure, let's do that." And well, when you compute how many grains of rice you need on the 64th cell, and on top of that, you just don't need the grains you put on the 64. You also need all the grains you put on the 63rd and 62nd and so on. What you find is quite remarkable. So let's do it one step at a time. So here is the same problem, but now with numbers. So on the first cell, we put 1 grain of rice. On the second cell, we put 2. On the third, we put 4. So we double every time. So 4 becomes 8, becomes 16, 32, 64, 128, and so on. And we keep on going. So when we get to the 20th cell, all right, remember the 64, 8 by 8 is the number of squares on the chessboard. So on the 20th square, you're going to put 524,288 grains of rice. That's quite good. That's several pounds, several kilos of rice. Well, if you keep on going and you go to the 30th square, you're going to need 530 million grains of rice. And so I think you see where we're going with that. When you go to the 64th square, you get this huge number. So that's 1,000, million, billion, trillion, quadrillion, quintillion, 9 quintillion grains of rice. Well, when you do a quick computation of the weight of that, and you compare that to the crop of rice on Earth in a single year, then that number is much larger than all the rice produced in 1 year on Earth. So there's no way you would be able to come up with such a number. And the reason for this is that this growth here, when you have something that doubles at regular intervals, goes extremely fast. It grows extremely high and very quickly. So let's take a look at that with a graph. So those of you who might be not very familiar with graphs, don't be scared. This one is very easy to understand. What we have here is the number of squares, so 5 squares, 10 squares, 15. And here, that scale on the y-axis is the number of grains of rice. So 1, so 1 square, 1 grain of rice, 2. And the reason that this looks flat is because at 15, 16, 17, the number that you need, the number of grains of rice, is so high already, more than 60,000, that it flattens everything that takes place here. So see, this is 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. And so you see that because this number is so big, we have to crunch all these that are pretty big numbers nonetheless. We just saw them, but they appear flat even though they're not. There's a growth going on here. But the last squares here really impose, create a number that overshadows all the others. And that's going up to 15. If I go to 25, which is not that much more, you see that 16, 17, that number that I had here, 15, 17, is now here. That little dot here represents the quantity that I had here. But because this quantity is so small compared to what happens at 25, that I'm squishing down the scale. So here, all these look like they're really not growing fast at all, even though they are. And the reason is that the last one is always so large. Actually, it's twice as large as the one before, twice as large, 4 times as large as the one there, that this is always going to look flat. So we call these exponential growth. So this curve is an exponential. We also, another way of saying it is that we'll say this quantity grows exponentially. And when we go to the last one, where I have 64, so that very huge number that we saw is right here, 9 something. And that number is so huge that everything else in comparison looks small. So, so we need to understand exponential growth because it's directly related to Moore's law. So see this particular shape. So mathematicians have called this. They have a nice nickname for it, which is a hockey stick curve. A curve that looks flat for forever, and then suddenly at the end it goes up. And that's what an exponential growth here. So remember, I have this little dot is 1, 2, 4, 8, 16. But, you know, 2 to the 20 is about a million, so this is a million here. But compared to 10 to the 18th, this very, very large number, everything here is going to be flat. So, so that's representing an exponential growth, so a hockey stick kind of curve. And in order to show the information differently, in order to better see it, we need to use a different scale. If I go back, see the scale that I have here, actually going back here, the scale that I have here, 0, 2, 4, 6, 8, it is linear. 0, 5, 10, 15, 0, 10, 20, 30, 40, 50, 60. If I multiply 1 by 2, see if I multiply 10 by 2 I get 20, if I multiply 20 by 2 I get 40, and so you see there's a linearity going on here. In order to see this better, we somehow have to change the scale. The scale is not appropriate for seeing exponential growth. So what I'm going to do is look at the scale that has a very, very different property. So here I've put it down horizontally, but actually we're going to use it for the y-axis of our graphs. And that scale is particular in the sense that, well, all the quantities that I want, so this, we're going to measure the amount of grains using this scale. So 1 grain, 2, 4, 8, 20, 40. What you see that is interesting, and I've highlighted that with these little lines, when I multiply a quantity by 2, 2 times 4 is 8, 2 times 20 is 40, 2 times 100 is 200. The difference on the scale between a number and its double is always going to be this. See, the distance between 2 and 4 is going to be this, because 4 is 2 times 2. The distance between 1 and 2 is going to also be this. The distance between 8 and 16 is going to be the same interval. So the scale, we call this a logarithmic scale, is a scale where a number and its double are always going to be a fixed distance away. So see, 100 and 200, that distance. 200 and 400, that distance. 400 and 800, that distance. So if you do that and you use this for the y scale, this diagram becomes this. And so now you see here that 1 10 to the 0th power is 1. This is 10,000. This is 10 to the 8th, which is 100 million, and so on. So this curve that we had here, where we really see well what happens at the end, but we have no idea of what's going on here. So suddenly we see that there's a nice relationship. And what is interesting is that the distance between two of these dots, two dots that follow each other, is always going to be the same. Why? Because I'm multiplying the number of grains of rice by 2 when I go from a square to the next square. So if I'm multiplying an amount by 2, the difference between that amount and the next one is going to be fixed, and it's the same one throughout. So each little step that I'm taking here corresponds to multiplying a quantity by 2, and it's going to be the same no matter where I am. And so this logarithmic scale here, and I haven't changed the scale there, 0, 10, 20, that's the number of squares, then suddenly I can see exponential growth very nicely. They're straight lines. So that's the beauty of the logarithmic scale, is that it shows exponential growth as straight lines. So it's a very nice way of recognizing if something is exponential or not. You display it in a log plot, and you just, if you have a straight line, then whatever you're looking at is exponential. All right, so now we are back to Moore's law, and that's the law that Moore discovered when he was asked to predict the future for the next 10 years. He just looked at how many transistors were put inside various processors, and what he found is that at regular intervals, Intel came up with different processors, and every time the quantity of transistors that could be integrated, so that means that the technology had advanced enough that they could make the transistors smaller and faster. And if you look at the integration, you see that although this is not straight, it's fairly straight. And what is interesting is that axis, that scale here, is logarithmic. See, I'm multiplying by 10 here at regular intervals. So 1,000, 10,000, 100,000, 1 million, 10 million, 100 million, 1 billion, 10 billion. So you see that this curve here is showing that at regular intervals, and typically it's 18 months, every 18 months the number of transistors doubles inside a processor. So that's the law that was governing the growth of microprocessors in terms of power, in terms of what they could do. And if you have more transistors, then you can operate in bigger integers. You can have more complexity, so you can put more cache memory, for example, inside the processor. You gain on many different respects. So that's Moore's law. So Moore's law is one that says that the growth of technology is exponential, and that processors follow this rule, so that every 18 months you can expect processors to have twice as many transistors, and therefore the performance, even though the performance will not double, then it will follow pretty closely that. So you should have an increase in performance. And that was great for Intel, and that's why Intel has been a successful company, is that new processors and more transistors, therefore they could work. They could process more information. At the same time, the transistors were smaller. Intel was also very good at making them operate faster, so they could speed up the clock signal of the processor and the computer, and therefore more information could be processed in a given amount of time. So of course, if you had a computer, you wanted a new one after a while so that you could spell check your documents faster, so that you could have more fancy operating systems with windows that would animate when you would close them and so on. So, so that's an important law for us to know. So Moore's law applies mainly to transistors in processors, but what is amazing is that people have found that this law also governed the growth of 60 different other technologies. The amount of bits that you can put in memory chips, for example, follows that. People have also applied it to economics. So you have this, whenever you have something that doubles in some quantity that you can measure, and if that quantity doubles every fixed number of months, then and over some periods of years, then you can say there's an exponential growth going on here. So and technology especially has been one where this has happened. And one person who's done a lot of work with that and has shown Moore's law applying in many different areas, if you are interested, is Ray Kurzweil. Ray Kurzweil was a professor at MIT, researcher, has done a lot of work on computers, on is really looked at is a futurist in some ways. You can think of Ray Kurzweil as somebody who's looking at the past, extrapolating what he observes, and from that predicting the future. And his predictions have been very often. He's been in that business of predicting the future for 20 years at least, and he's been right a huge amount of time. So he's somebody with a great vision. He's now at Google. He's one of the chief technology officers at Google. But what he did here is that instead of looking at just the transistors, he decided to look at the calculations per second, per 1,000. So if you have $1,000, for example, in 1900, if you had $1,000 and you could invest it in some form of computation, could be hiring somebody to do computations, for example, how many calculations per seconds could you do? Well, that's that number, 10 to the minus 5. So that's, much less, this is 1. And so he plotted that, and then the electromechanical technology came on board, and so you could suddenly use punch cards. And so if you look at time and the years going by, you see that technology changes. Punch cards, relays, vacuum tubes, transistors, integrated circuits. And the trick also here is, if you look at the scale, this scale is logarithmic. The interval of time between here and here, it corresponds to multiplying by 10, multiply by 10, multiply by 10, multiply by 10. So you have a fixed interval between two numbers that are one 10 times greater than the other. So logarithmic scale, linear scale here, and something that is extremely flat. It's a bit of a curve, but it's pretty close to being a straight line. So you see here that this actually follows Moore's law. You have a doubling of the number of calculation per every fixed number of months. And I haven't computed that here. But so Ray Kurzweil has looked at many different, and he's gone back thousands of years and looking at the evolution of mankind, and found out that actually if you look at the evolution of what we could do, what we could accomplish in terms of amount of work since the beginning of time, since we have records, follows a straight line. It's quite remarkable. So Moore with transistors covers really the end of that curve, and Kurzweil in this one shows that actually it extends more. You just have to look at something different. So Kurzweil's genius was to look at the right amount here. So the amount that he's measuring is the number of calculations per second per $1,000, and the $1,000 will also fluctuate as a function of time. All right, so the question is Moore's law dead? And so every so often you're going to see that in newspapers. There will be a claim that Moore's law is dead, or a claim that it's still, we have a new breakthrough, we have new processor being output by some company, and it is maintaining Moore's law, or maybe not. So a few months back, I was at a conference on supercomputing, and I got this graph there, and it is interesting because it's looking at several quantities, linear scale in years here at the bottom, logarithmic scale here, so the quantities are plotted against a logarithmic y-axis, and the number of transistors, which is what Moore had been looking at. So if you start in 1970 something, 1970 or so, you see that the number of transistors as a function of time is growing very nicely exponentially. So Moore's law in terms of number of transistors that you can put in a device is keeping up. So it is not dead. So that's 2015 projected to 2015, and up until now that is working. Single thread performance. So that is interesting. This is single thread performance. It's another way of saying a single program running on one core of a machine. So the performance of that. And what people have found is that the performance is plateauing and actually decreasing here. So actually the performance, and we'll talk a little bit about that. The frequency of the clock that makes the processors operate. What we're seeing now is that we have reached the maximum. So that's back to what we were I mentioned at the beginning of this this lecture, is that we have reached the maximum clock speed for today's processors. 2 gigahertz for laptops, 4 gigahertz for servers. That's pretty much the max. And the reason that we've reached the maximum is that if we were to make the processors work at a higher clock speed, they would start melting. They would get so hot that they would start melting. And so we can't. And because we have more transistors now inside processors, we see that we actually have to decrease, because we're getting so many more transistors, we're doubling, quadrupling the number of transistors, that we actually have to reduce the clock speed in order to make these processors work and still operate correctly without melting. The amount of power, so that's related to clock, and we see that, so one is related to the other, and so the amount of power, there's so much power, so that's heat. When you look at power watts, that's the amount of heat that is generated by your processor when it's running. If you were to, I think you might be able to discover that when you have a laptop that is doing some very intense graphic operation, or maybe you're playing a game, or doing, looking at some a movie, you're going to find that your laptop is getting quite hot, and it's because the processor is doing a lot of work, moving bytes around. So every pixel on your screen is a collection of bytes, maybe 3 bytes each. And when you have a movie, all these pixels, the whole screen has to be refreshed 30 times a second. So there's a lot of movement inside the processor and inside the computer, and the processor is working very hard. And so the total amount of power that you can dissipate, you want to limit it so that, of course, your laptop you don't want to be burnt by your laptop. So we have reached that limit here. So, and you see that before that, the growth of the typical power was increasing nicely in a straight way, not quite linear, but in that graph, but quite nicely. So it was exponential, but now it's plateauing. And the number of cores, we talked about that when we were talking about von Neumann. The number of cores that stayed the same until like 2005, when it really started going up to 16. So that was an effort to have 16 cores, but actually we're going to stay at a small number. So actually no, 10 to the 2 is 100. Yeah. So that's 10, 20, 30. So that might be 64 actually right here, 64 and maybe 16. So we see that there were efforts, but we've reached the maximum number of cores here, and that limit is more has to do, as we saw before, it has to do with the fact that we don't know how to write programs that will efficiently utilize the processors so that they don't they can operate in synchrony, accessing the memory, so they will not block each other. So is Moore's law dead? Not for transistors, but actually we can say that yes, it has died for other quantities, like the performance, the number of instructions that can be executed by one processor. We've plateaued here. The clock speed, we're plateauing. Typical power. So something has to happen. Something has to happen, and that's what we're going to discuss right here. So what are the implications of all that? So when you look at Moore's law, especially when you look at Ray Kurzweil's graph, you see, I'm going to go back to that. You see that there's an amazing trend, and the trend, it doesn't matter here whether we were working with punch cards, or we were working with electrical relays, or when we moved to vacuum tubes or transistors. And you have to realize that it's very different. A computer with relays is very different from a computer with vacuum tubes, very different from a computer with transistors. So they're really different machines. However, when you look at the amount of calculations, which is a nice unit to use for measuring them, you have a very smooth growth here. This growth doesn't really matter what the technology is. So Moore's law in some ways rides the technology, so that it doesn't really matter what the technology, what it's saying is that there's a doubling of some quantity over time, and it doesn't matter what the technology is. So right now we're seeing that we are kind of plateauing in many areas. If we believe that Moore's law is going to continue, that means that there should be, right now, somebody will invent something new very quickly in the near future, and that will become the new technology used in computers, which will make Moore's law continue. That's one way to look at it. So when I say Moore's law rides the technologies, is that it's agnostic to technologies. It just says that the amount of computation somehow will follow Moore's law. So because we are still very good with transistors and making them smaller, it's possible that some technology will appear in the very near future that will make us continue with the trend. We seem to be at the end of an era in technology, and a slump is appearing and a growth rate of many curves. So that's, in some ways, this will validate the assertions that some are making that Moore's law, we're at the end of Moore's law and Moore's law is dead. So that is true for some quantities, but not for others. And so, going back to point one, a new technology must be discovered in order to maintain the exponential growth that we have seen in computers. And if we believe that the past is a good indication of the future, then very likely this will happen in our lifetime, and probably in the next 5 to 10 years we can expect some discovery to allow us to continue that growth, where computers are going to become even more powerful. We'll be able to compute much more, process much more information in a given amount of time. So it must be around the corner. So that means that in your lifetime, if you're in your 20s, there will be remarkable discoveries that will make the toys that you're playing with that much more interesting and more fun.